Measuring optical signals in the femtowatt to nanowatt range can be very challenging. Signal levels this low are lost in typical detector noise levels and swamped by background light. The noise floor for photodiode detectors operated with a small bandwidth, say 10 Hz, is in the order of 1 picowatt. Standard steps to improve signal-to-noise ratios include further narrowing of the bandwidth by filtering or averaging over time, which should reduce random noise by averaging it out. But these only provide a small additional reduction in the noise level. In order to achieve significant improvements in noise rejection, we need to turn to a lock-in amplifier. Lock-in amplifiers can improve noise rejection by 3 orders of magnitude or more. They can also provide background signal rejection that's several orders of magnitude higher than the noise rejection. Lock-in amplifiers achieve this outstanding performance by employing a technique called homodyne detection. First, the signal to be detected is modulated at a specific single frequency. Then, a clean reference signal with the same frequency needs to be provided. In the lock-in amplifier, the signal to be measured is multiplied by or combined with the reference signal and then integrated over time. This results in an extraordinarily narrow effective bandwidth. Signals at all frequencies that differ by even a small amount from the reference frequency will result in a net integrated value of essentially 0. Since detector noise is white, meaning its power is spread across a broad spectrum, the noise amplitude component at the measurement frequency is very low. By then confining the measurement to a single frequency, detector noise is reduced drastically. In a similar fashion, background optical signals, primarily DC or line frequency, are similarly rejected by the lock-in amplifier. The key to high performance with the lock-in amplifier is maintaining a precise match between the modulation frequency of the signal to be measured and the frequency of the reference signal. In optical applications, this precise match is readily built into the architecture. Many low-level optical signals that need the benefits of a lock-in amplifier are DC or very low-frequency signals. In these applications, an optical chopper is used to modulate the signal. An optical chopper is simply a spinning disc that's divided into vanes and windows. The chopper disc is positioned in the optical beam path so that as it spins, the beam alternately passes through the windows and is blocked by the vanes. The size of the beam should be smaller than the width of the vanes in the windows in order to achieve 100% modulation. In optical choppers, the reference signal is easily provided by using an optical interrupt switch, essentially a small light source and detector placed on opposite sides of the spinning chopper to sense the rotation of the vanes and windows. This optical interrupt switch can be located at any radial location on the disc that doesn't conflict with the passage of the optical beam that we're trying to measure. The reference signal provided in this manner will by definition be a precise frequency match for the optical signal to be measured. For optimal performance, it's still important to tightly control the disc rotation speed to minimize jitter and other artifacts. A high degree of uniformity in the disc geometry is also critical. Here, we can see the system schematically. The optical signal is modulated by the chopper, and the chopped beam then reaches the detector together with unchopped noise and background light. The detector's output signal is combined with the reference signal from the chopper in the lock-in amplifier, where the two signals are multiplied and then integrated over time to extract the original signal to be measured. In setting up the system for use, the chopper should be as close as possible to the optical signal source so that the modulation is applied exclusively to the signal of interest and not to any unwanted background signals that may be present. Ophir's RM9 family of sensors incorporates a compact, dedicated lock-in amplifier, an optical chopper, and a selection of sensitive detectors in an easy-to-use system for measuring ultra-low signal levels, even in the presence of much larger background noise. Detector types include silicon photodiode for the ultimate sensitivity in the UV and visible spectral regions, pyroelectric detector for broadband sensitivity out to 12 micrometers, terahertz detector utilizing a proprietary absorption coating. This sensor family provides high performance for a wide range of demanding applications such as spectroscopy, terahertz detection, free space gas analysis, atmospheric studies, Raman scattering, and many others. Contact Ophir directly or via your local Ophir representative to see how we can help you with your application.